In today's lecture, we're going to discuss bone tissue. Specifically, we'll focus on three different things. So we're going to focus on cartilage, then bones, and then finally disorders of the bones. So let's go ahead and get started by a discussion on the cartilage. So what are the major structures in the body, the adult human body, that are cartilage? Well, there's a bunch of them, as you can see on this diagram here. And cartilage, as we'll discuss in a second, is broken into three different types of cartilage. So the first type is something called hyaline cartilage. And you could see that right here, sort of highlighted in blue. If you look at the diagram on the left, you can see that hyaline cartilage is also often associated with the ribs. Right? So you'll see it over here in the ribs. You'll also see it in the articular joints. Right? So whenever you have a joint here, sort of in the articular joints. The second type of cartilage is something called elastic cartilage, and you'll see that in green right over here. And if we say, okay, where does that, where is that actually held? You can see that's the cartilage of the external ear. So you'll see that right here, as well as the epiglottis over here on this diagram on the right. The final type of cartilage we're going to discuss is something called fibrocartilage, and that's indicated in red here. And the fibrocartilage is cartilage that we often find in the vertebrae. So you can see that down the spinal cord here. We'll talk about each of these three types of cartilage a little bit more in a second, but I just want to show you in a diagram to show you where they're located. A couple side notes, before we go to the next slide. One thing to keep in mind is the younger you are, the more cartilage you have, and as you age, this cartilage is replaced by bone, which, sort of makes sense. A second thing is that we want to consider a word here. And so this perichondrium is a word that means it's dense, irregular connective tissue that surrounds most of the cartilage. And really, it's very important, and has two very important functions. So one of them is it causes the cartilage to resist outward expansion. So the cartilage doesn't just become smashed and expand all over the place. It has to maintain its form to some degree. That's the first one. And the second function that it has, I would sort of lump these two together here, growth and repair. Right? It's involved in growth and repair of bone, and we'll see that in a second. As we see, there's certain cells located here that help with growth and repair. Okay, so let's go ahead and proceed. So what are the three types of cartilage? Well, there's three types, and before we say that, the general statement we want to think of is this, that cartilage is a type of connective tissue, right? And it consists of cells called chondrocytes. And there's an abundance of these sites in the matrix. And then one thing that's important to note is, in contrast to connective tissue, each chondrocyte is located in a space in the matrix called the lacuna. And this literally means lake or cavity. We'll show you pictures of this in a second, and you'll also see these in lab. The second thing we want to note is that that cartilage has a matrix, right, of fibers and a jelly-like ground substance. It has a lot of sugar molecules, a lot of carbohydrates in it, and it holds a lot of water too, which helps convey the function that cartilage often has. Again, a key concept throughout anatomy, that function follows form. Okay, so the first type of cartilage is hyaline cartilage. And you can see here when you look at this slide, it has sort of a glassy-like appearance to it. And that's a key hallmark of hyaline cartilage. So if we look at this, you could see that, again, hyaline literally means glass, right? You'll see spherical chondrocytes. Okay, you'll see those sort of up here in the lacuna. You'll see that. You'll also note that the collagen units are not visible. So there are little tiny collagen fibrils here, but you don't see them at all. And so my point is, you don't see any like rope-like structures running through the matrix. Rather, you could see that the matrix, as you see it right in here, is very, very clear. A fourth thing we want to talk about, the ground substance holds lots of water, and I mentioned that a second ago, and really the function of this is that it helps this type of cartilage be compression resistant. You'll notice that cartilage has a lot of forces pushing on it, and this really helps it be compression resistant. Examples of hyaline cartilage are joints, the sternum, structures of that nature. Okay, the second type of cartilage we want to talk about is elastic cartilage. And here's sort of a picture of that. You can see a lot of elastic fibers running through it. So you'll see that here, all these sort of like real dark purplish, rope-like structures, okay? They're running through it. Here you can actually see those, right, throughout the ground substance. Okay, so it's very interesting. You can see we have chondrocytes here in the lacuna still. And then couple notes, right? It's very similar to hyaline cartilage, but here's the difference. It contains those elastic fibers. And so hence, not too creative here, but elastic cartilage is much more elastic, right? For lack of a better word, than hyaline cartilage. And you could notice that in the fact that you'll see this in the epiglottis as well as the structure of the outer ear. The third type of cartilage we want to focus on is something called fibrocartilage. And in fibrocartilage, you see a lot of collagen fibers. And those are these like light pink looking structures, these thicker ropes that are coming through. Remember, collagen fibers used for strength. And so a couple notes on this. So this type of fibrocartilage is very unusual in the sense that it resists compression, right, pushing the cartilage together, as well as tension forces, which are pulling the cartilage apart. So it's very strong in both of those regards. The second thing, again, is those collagen fibers I mentioned a second ago. Sort of some examples where you would see this is the meniscus of your knee, and then other examples I have listed there. So it's a very interesting type of third cartilage. Okay, so those are the three types of cartilage that you want to be able to, sort of recognize and be able to explain a few points on. Okay, so how does cartilage grow? Well, there's two types of growth with cartilage. The first one is oppositional growth, and this means growth from the outside. Okay, so there's chondroblasts in the perichondrium surrounding the bone, and that helps produce, surrounding the cartilage, and that helps produce new cartilage. The second type of growth is interstitial growth, and this is growth from the inside, right? So growth of the inside. And here we have chondrocytes within the cartilage that divide and secrete a new matrix. So two different types of growth happening at once, which is very interesting. Another thing to note is that cartilage stops growing when the skeleton stops growing. That's why when you have injuries to the cartilage, if you're an athlete, often, not always, but often that requires surgery. Okay, talked a little bit about cartilage. Let's move on to bone here. These are the objectives or the learning outcomes you want to achieve with bone. Okay, so are the bones of the skeleton organs, right? Are they an organ, the way we define an organ? If you think about it, we said an organ is a bunch of different types of tissues, right? So a structure that contains a bunch of different types of tissues, and that structure, along with those tissues, helps execute a common function. So if we use that as our working definition, which we had used before in this course, let's look at this. So bones contain several types of tissues, right? They're dominated by connective tissue, right? The bone connective tissue. But you'll see it also has nervous tissue, right? We have blood, connective tissue, contains cartilage, and then also epithelial cells. In other words, the blood vessels, right? Lining everything. And so based on that, we have all these different types of tissues, in one structure in the bone, and it helps execute a common function, which we'll see those on the next slide. So yes, definitely. We would say that the bones of a skeleton, right, are organs. So definitely yes, based on this definition. Okay, so going on with that, what are the functions of the bones? What are the functions of these organs? One is support. Some of these are a little obvious, right, but it's worth mentioning. So one is support. Second one is movement, right, along with the muscles, with the skeletal system. A third one is protection of the underlying organs. Another one is mineral storage. Very important, actually. We don't really think of that all the time at first glance, but the bones help serve as sort of a reservoir, for different minerals, and these minerals can be released at different times to serve different functions in the body. Blood cell formation, right? Bone contains red marrow to help form blood cells, and then energy and metabolism. Okay, so we'll talk about that a little bit more later on. So these are the I guess 7 or 1, 2, 3, 4, 5, 6, right? The 6 functions of bone that you want to make sure that you put to memory. Okay, so what are the components of bone? Well, if you look at bone, there's 2 major components that you want to see here. Okay, so there's 2 major components. The first one is that bone is composed of organic components. About 35% of the total weight of a bone is organic. When we say organic, we mean things like cells, we mean things like fibers, things like ground substance. And what does this do? This contributes to flexibility and tensile strength. So it's very interesting. And to sort of prove this point, it's very, very sort of neat, actually. We'll try to demo some of this in class. Maybe not both of these, but we'll try to demo one of these. And you'll see that if you cook some bones, so I'm envisioning the bones inside that chicken, right? If you cook it, those bones are really hot for, quite a few, maybe 20, 30 minutes. What's going to happen is you're going to burn off the organic components, and all you're going to leave behind are the mineral deposits in the bone. So the bones will still have their strength per se. In other words, they're not going to be like a rubber band, but you can break them very easily because the organic components, what do? The organic components you burnt off aid in flexibility and tensile strength. So you'll have very brittle bones if you burn off the organic components. The second component of bones is the inorganic part. So these inorganic components, about 65% of the total mass of a bone. And these inorganic components, these minerals, etc., help with the hardness of a bone and helps them resist compression. So on the other hand, if you take a bone, right, let's say you put it in a dish of vinegar, so pretend this is a dish of vinegar, you put a bone in there, what's going to happen is the vinegar is going to eat away at these inorganic components, and all you're going to have left is actually the organic part. And so the organic part by itself is going to be strong, right, flexible, but it's not going to be very stiff or rigid. So you could actually take that wishbone once you burn off, or not burn off, excuse me, once you erode the mineral salts, right, with vinegar, once you erode them, you could take this wishbone right here and you could literally take it and tie it in a knot because it's very flexible. So that's sort of a neat thing there. Those are the two main components of bone. Okay, so what types of cells are found in bone tissue? Well, there's three types of cells in bone that either produce bone or they maintain bone. There's osteogenic cells, and these are stem cells that differentiate into osteoblasts. Remember, stem cells, differentiate in different types of cells as well as maintain their own stock of stem cells. We call it the asymmetric cell division of stem cells. Second type of cell is something called an osteoblast, the one I just mentioned at the end of the first one there. And these actively produce and secrete the bone matrix. The bone matrix is called an osteoid. The final type of cell is something called an osteocyte, and these help keep the matrix healthy. Now, a little side note here. We have other cells that we haven't discussed yet called osteoclasts. These are found within bone tissue, but they're responsible for reabsorption of bone, and they're derived from white blood cells. And the way they, reabsorb bone is they help erode it, right, by secreting hydrochloric acid as well as lysosomal enzymes. So those are the different types of cells that are involved in bone tissue. Okay, let's move on to sort of a larger topic here, right? Gross anatomy. So how are bones classified? There's a few different ways to classify them, but let's look at one system here. Okay, so one type of way to classify it, and here what we're doing is we're taking the bone of the skull and we're sort of blowing it up, you could see here. So we're taking this right up here and we're sort of enlarging it, right? We're looking at this area here, and then the bottom picture is this top little square further enlarged in the bottom, so you know what you're looking at. Okay, so how do we classify it? Well, we have some bone that's compact bone. Okay, we'll talk about that more in a little bit later. And then we have spongy bone, the trabecular bone, it's called. I often think it sounds like, if we look at the bottom picture, we're going to blow it up. We see all the little holes in the trabecular bone, right? Sort of spongy bone, a lot of pores. I sort of think that, it sounds like Dracula instead of trabeculae or trabecular bones. So I just say this because I think of ways to remember things in anatomy. There's so many things to remember. So I think, Dracula. In other words, if Dracula was, eating spongy bone, he'd be punching a bunch of holes in it with his teeth. So that's sort of how I think of it. Trabeculae, has all these different little holes, in the spongy bone. So yeah, if it works for you, use that. If not, think of something else. But that's spongy bone. Okay. Also, you'll notice within all these little holes here, these spaces are filled with either, so these spaces right in here, right, either with a red or yellow bone marrow. The red bone marrow is helping to derive blood cells. The yellow bone marrow is helping with sort of genesis of fatty tissues. Okay, another way that we can say, okay, gross anatomy, how are bones also classified sort of in a different way, right? Different little characterization system. And this is one way. So we have 4 different bones up here, right? 4 different classes. The first one, letter A, right, is called the long bone. And this specific example is the humerus, right, of the arm. So long bone's a category. Humerus is an example of that category. And so what exactly is a long bone? Well, one thing I want to know is they don't have to be long per se, right? So we do think of the humerus or bones of the arm, this upper bone of the arm being long. We would obviously think of, a bone in the leg being long. I don't know if we think of bones in the hand as being long, right? The fingers, but those are also long bones too. So what does it mean by long? So what we mean is this. We mean they're much longer than wide. And there's no exact cutoff, right? But much longer than wide. Another thing we mean is that there's a shaft. Okay, so you'll see the shaft is the center portion from here to here, right here. But there's also 2 distinct ends. So you'll see one end here, and then you'll see the other end right up here. Examples of these are limbs and fingers, as I mentioned before. Okay, let's go on to B. So letter B, what is that? That's something called a short bone. Again, this is the talus. That's an example, right? But the category is short bone. And what do these mean? Well, short bones basically are roughly cube-shaped. Okay, so roughly, we're being very general here. Examples of this are the wrist and the ankle, or bones in the wrist and bones in the ankle. Okay, the third category, C, is something called a flat bone, and one example of a flat bone is a sternum. And what does this mean? Well, as they say, flat bones are flattened, right? So not too original there. They're thin and they're somewhat curved, right? So there is some curvature to them, not perfectly flat. Examples of these flat bones could be cranial bones, ribs, sternum, scapula, things of that nature. Okay, let's move on to letter D, the last of the four types of bones with this classification system. So D, it's basically everything else, right? So irregular bones. Bones like the vertebra, bones that don't really fit in a given category, honestly. Basically, it's like everything else goes in here because they don't have any uniform shape. And so what do we mean? Okay, so various shapes, the leftovers, right? Everything goes in this category if it didn't fall one of the other three categories. And examples, the vertebra, the hip bone. You can see they look very different from each other, right? So here's a vertebra. Looks very different from the hip bones up here. But again, all the odds and ends go in this category. Okay, what is the structure of a typical long bone? Something we want to look at here. Okay, so typical long bone. So we're looking at each of these categories a little more detailed here. Okay. Okay, so the first element of the structure of the long bone is something going to be called the diaphysis. And that basically is the shaft region. If you move on to the next region, we have two ends that are called the epiphysis. We have the proximal epiphysis on this particular bone, right? Closer, up towards the origin of the bone where it leaves the abdomen. And then we have the distal epiphysis, again, sort of going the distance, right? If this was in the arm, closer towards the fingers, relatively speaking. There's some other components as well. You'll notice we have something called the epiphyseal line. And this is something where basically it's what we call a growth plate, but it's a growth plate that has sort of sealed, right, in an adult. That's what that line is. You'll notice that on the proximal epiphysis at the very top, we have something called articular cartilage, right, where you're going to have a joint. We have the periosteum, which is basically that irregular connective tissue that we mentioned a while ago that's coating the bone, right, around the bone. We also have numerous arteries running through the bone, right? Various capillaries running through. You'll notice there's a center cavity, so these bones are hollow in the center a little bit. And that's a medullary cavity lined by endosteum. Something that's very interesting we'll talk about a little bit later is you think that the bones being hollow would be bad for strength. But actually, from an engineering point of view, and we're not going to go into that, but from an engineering point of view, actually having the center hollow increases the strength of the bones. So it's sort of an interesting phenomena. And it's biologically relevant in the fact that you can have, substances stored there, like yellow bone marrow, something like that. So it's very practical from both an engineering point of view in terms of strength, but also from a biological point of view in terms of getting blood where it needs to be. Okay, what is the structure of the short, flat, and irregular bones? I said, what is the structure instead of being plural, making it singular, right, for structure, because I'm saying the same general structure applies to these other ones. So I'm going to say some notes on them. So they contain bone marrow, but no marrow cavity, like you saw in the previous one. And then also there's internal spongy bone of the flat bones, right? So a lot of bones of the head or the cranium are flat bones, and we see that spongy bone in between, the other types of bone that are there. So in between the compact bone. So and we call those diploi. That's what we call them. So it's sort of a neat phenomena that all these types of bones share. So I encourage you to think of these three types of bones sort of in a category together in terms of talking about structure. Okay, so is bone optimized for stress and biological operation? I mentioned before that the answer is yes and yes for each of those. This just helps show you a little diagram here. It shows you that, if you have load basically over here, right, so body weight over here, this is the head of the femur over here to give you the orientation. You could see that, if we have compression, right, so we have compression here, we could have tension, right, the pulling apart of the bone. And you could see that from an engineering point of view, actually there is a point here where there's something called a point of no stress. So literally, it's like, almost I think of it as like a scale, right, and you have the same amount of weight on each side of the scale, like an old-fashioned scale where there's like, two bags of gold on either side or something like that. Really here, there's very little stress there. So we think of bones as being under stress a lot, which they are, but to some degree that stress is minimized at certain locations, which really helps prevent them breaking. Obviously, if you're going perpendicular to the bone here, sort of from this direction here, this way, horizontally across the screen, that type of stress can lead to a break. We'll talk about that later on in the course. The bone's not really designed for that as much, and you could tell that if you're an athlete. Okay, so what is the microscopic structure of compact bone? So a few terms we want to talk about here, and really what you see is the big picture on the top, and then sort of I guess a zoomed in picture here on the bottom left, and then the bottom right here, these two pictures are just zooming in even further on sort of the central canal and the surrounding regions. So one thing I want to show you is that we have compact bone on the outside, right? We have spongy bone on the inside, and the inside of bone is a little more hollow, right? Which allows for blood vessels to go through, etc. So a few things I want to point out here. One is that we have something called an osteon. A haversian system is another way to put it, and that's referring to this whole region right here. We'll zoom into this now in a second, but I just want to mention that's the whole region there. And so let's zoom in and talk about, well, what is that? What is there? In the middle is something called basically a central canal or a haversian canal. And this is where you have blood vessels running through, right? So an opening where you have blood vessels running through. Just around that, and I'm going down here now, you have lamellae. And these are basically the things that look like rings on a tree, right? Like tree rings. As these, excuse me, as the bone continues to mature, right? Actually, what happens when the bone grows, it's growing from the inside out often, as we mentioned before. Excuse me again. I lose my voice. It's growing from the inside out, or it's possible to grow from the inside out. So as it grows, basically this central canal, right, which is right in here, right in there, that actually will get smaller over time as these lamellae sort of grow into it. So that's sort of a interesting fact to note. Okay, so what are some other things we see in this picture that are notable? Well, here you could see that we have these things that are running at right angles, right? They're perpendicular to the central canal. So here's the central canal all the way through, right there. And then this is running perpendicular to it at a 90-degree angle. And those are things that are called perforating canals or Volkmann's canals. And those are allowing blood to reach the internal parts of the spongy bone. What are some other things that we see here? You could see on the left here, we have these lamellae here, and these are the circumferential lamellae, excuse me, and these are sort of the outer tree rings around the outer edge of the bone in the compact bone. So that's another thing to note here on this slide. Okay, if we go down here, we see some other structures too. Okay, so if you focus your attention on the bottom left here and sort of the arrow that's flashing back and forth, you'll see that we have these canaliculi. And what those are, right down there on the bottom left, those are little passageways that are connecting the different lacunae structures to one another and to the nearest capillaries, such as the central canals. And then within each of those, you have neighboring cells that are called osteocytes that touch each other, and they're forming gap junctions. Think about it again. What does a gap junction do? Right? What does a gap junction do? Remember, that's where the cytoplasm of neighboring cells are interacting, and they're passing nutrients as well as other molecules back and forth. So that's a structure that you want to particularly take note of. Okay, on the right-hand side here, you'll see that we have something called an osteocyte within a lacuna. And if you look further, you'll see that we have a central canal here, right here. We have the osteocyte within the lacunae right here. And then we have things called interstitial lamella as well. So those are different structures that you want to focus on when we talk about the microscopic structure of compact bone. What is the microscopic structure of spongy bone? Well, it's a little less complex than compact bone, so there's a little bit less to talk about. The trabeculae contain layers of lamellae and osteocytes, but they're too small to contain osteons, which actually I think I forgot to point that out on the previous slide. So let's back up 1 second really quick here. And let's go ahead and take a look at our osteon. 1 second. Okay, our osteon, where is it here? It was the first thing I pointed out. So I did mention it actually, but I want to draw your attention back to it again. So we talk about the haversian system, which everything we were talking about is sort of included in that, right? If we have a single haversian system. And basically that unit is called an osteon. Okay, so I had mentioned it, but just to draw your attention to that again. Okay, so let's go back to the microscopic structure of spongy bone. Okay, so we talked about all that. Here's a picture of this here. Okay, you could see that here you have the marrow space, You have the trabecula right in here. We have osteocyte, those cells here, right, those osteocytes there, used for maintenance, right, repair. Remember osteoblasts, we have them right here. You can see those cells right here, lining sort of these marrow spaces. Remember osteoblasts, what are those used for? Those are used to produce the spongy bone. Whenever you have blast, that means we're producing the bone. So it makes sense that it's lining that marrow space there. Whereas osteocytes, that's maintenance of the spongy bone. Okay? And then again, we have this endosteum, which is sort of analogous to the periosteum. Okay, so after that discussion on bones, let's go over to a final discussion here on disorders of bones. And there's many, many disorders. There's a few in your text that I will not mention in this video, so you want to make sure that you read those as well. But let's talk about a few of them that are in your text. Okay, so disorders of bones. So the first disorder of the bone I want to talk about is something called osteoporosis. And you could see here that we have normal bone at the top, okay, and then we have an osteoporotic bone on the bottom. So a few things I want to say about osteoporosis. So what this is it's really a condition that's characterized by low bone mass. It's a deterioration of the architecture of the bony skeleton. You could really see that here with all these little holes sort of punctured throughout the bone. Looks like Swiss cheese. And then the one thing to note, it's sort of interesting, is the chemical composition of the bone matrix remains normal. In other words, different components are normal. But what really happens is bone reabsorption outpaces bone decomposition, which is a problem. Or sorry, not decomposition. I said that wrong. Bone reabsorption, right? So sort of destruction of bone by those osteoclasts, right? That outpaces bone deposition. That's the correct word, deposition. Sorry about that. Basically, again, as I mentioned, how does this happen? There's an increased number, right, of those osteoclasts, those cells that are involved in bone reabsorption. So you're losing bone overall because of that. Bones, when you have osteoporosis, become very porous, very light. The compact bone becomes thinner, very less dense. And then the spongy bone has fewer holes in it, right? Fewer of those trabeculae. So there's a lot of problems that are associated with this, and it affects the whole skeleton evenly, right? But areas that are subject to a lot of pressure are areas that are going to be sort of most visibly affected, right? That we can see. So those are areas of like the spinal cord, a lot of compression there, or major joints there, or major areas of movement in the body. And so, for example, like the femur, where it interacts with the hip joint. A lot of people will break that when they have osteoporosis. So that's sort of a problem. Really, it's something that affects women heavily, actually, as they go through menopause. Men develop it too, but to a lesser degree. And about 30% of American women will be affected by it throughout their lifetime. The main way that osteoporosis is treated is by giving someone vitamin D supplements and calcium supplements. Vitamin D because it's needed for calcium to be absorbed properly. There's other types of therapy as well, like estrogen therapy and things like that. But it's a little more controversial. Controversial might be too strong of a word, but certain types of therapy, like estrogen therapy and things like that, can actually increase the rates of certain types of cancers. Okay. The next thing we're going to talk about in terms of disorders is something called rickets. And this is something where an individual will have legs that are bow-legged. And really this is sort of, I would think of it as osteoporosis, but in children, right? So osteoporosis, but in children. In the 1800s, it was estimated that in the United States, maybe up to 90% of children actually suffered from rickets, which is an alarming number. And really, given that it's a deficiency of vitamin D and calcium, right, that causes this, this really coincided with, the ramping up of the Industrial Revolution in the United States. So a lot of children were working indoors, which led to child labor laws, sort of more of a sociological issue. But because they were indoors all the time, they were not getting the sunlight they needed, the vitamin D, to absorb the little calcium that they were getting anyway, because there's a lot of poor nutrition then. Once vitamin D started being added to milk, that really helped sort of curb, the rickets epidemic that was happening then. And I think that was around the 1930s or so. Now, one thing to notice is that there is a slight increase in rickets now in children, maybe, the age 6 to the early 20s. And that slight increase now is actually being due to the fact that a lot of children are being, kept indoors a lot, not playing outside as much as they used to, so not getting that sunlight to produce vitamin D to absorb the calcium they're getting. And then another reason is sort of related to that. And the reason that's really related to that is the fact that when children do go outside nowadays, they're constantly being lathered with sunscreen, right? All the time with sunscreen. Now, I'm not saying sunscreen is bad. We want sunscreen, used often, right? If a child will be outside for a long period of time because, lack of sunscreen exposes your skin to too much UV light from the sun, could develop into skin cancer. So we're not saying not to use sunscreen, but there has to be some periods where a child is outside where they're absorbing sun onto their skin to produce vitamin D, and that's not impeded by sunscreen. So you want sometimes where sunscreen is not applied. And they say, at least, it's a very minimal amount, but at least, 15 minutes 3 times a week or so to allow them to produce the vitamin D they need, to absorb the calcium they need. So these are some bone disorders. Your text actually, suggests other disorders as well that you should look into. But these are some just to give you an idea of things that could result. A lot of these bone disorders are things that are easily treatable, at least the ones that are environmentally provoked.